The final hour is coming, not tomorrow, not next year, but in 4.5 billion years, two giant galaxies will crash into each other. The Milky Way, our home, will meet Andromeda, our nearest large neighbor. And when that happens, the night sky will never look the same again. Picture this. You step outside on a clear night. You look up. Instead of the familiar band of stars stretching across the darkness, you see something else entirely. A massive spiral of light fills half the sky. It grows larger every night. It keeps getting closer. And there is nothing anyone can do to stop it. This is not science fiction. This is science fact. Right now, at this very moment, Andromeda is racing toward us at about 250 miles per second. That sounds fast, and it is. But space is so big that even at that speed, the collision is still billions of years away. If you are watching this video, you want to know what will happen when these two giants finally meet. You want to understand the forces that are pulling them together. You want to see what the future holds for our little planet, our sun, and the billions of stars that make up our home galaxy. And that is exactly what we are going to explore together. Before we go any further, if you enjoy learning about the mysteries of space and the wonders of the universe, take a moment to hit that like button and subscribe to the channel. It really helps us bring more content like this to you. Now, let us dive into one of the most amazing events that will ever happen in our cosmic neighborhood. To understand why Andromeda and the Milky Way are destined to collide, we need to talk about the invisible force that controls everything in the universe. That force is gravity. Gravity is what keeps your feet on the ground. It is what keeps the moon circling the Earth. It is what keeps the Earth circling the sun. And it is what is slowly pulling Andromeda and the Milky Way toward each other. But gravity alone does not explain everything. There is something else at work here. Something we cannot see. Something we cannot touch. Something that makes up most of the matter in the universe. Scientists call it dark matter. And without it, these two galaxies would not be on a collision course at all. Think of dark matter like this. Imagine you are in a room that is completely dark. You cannot see anything, but you can feel that there is furniture in the room. You bump into chairs. You bump into tables. You know they are there even though you cannot see them. Dark matter is like that furniture. We know it is there because we can see how it affects things around it, but we cannot see the dark matter itself. Both the Milky Way and Andromeda are surrounded by huge halos of dark matter. These halos are much bigger than the galaxies themselves, and they are incredibly heavy. The dark matter in the Milky Way alone weighs about 1 trillion times more than our sun. That is a number so big it is hard to even imagine. And Andromeda has even more dark matter than we do. All that dark matter creates an enormous amount of gravity. And that gravity is what is pulling the two galaxies together. It has been pulling them together for billions of years, and it will keep pulling them together until they finally meet. Now here is where things get interesting. When most people think about a collision, they think about a crash. They think about destruction. They think about things smashing into each other and breaking apart. But the collision between Andromeda and the Milky Way will be nothing like that. In fact, calling it a collision is a bit misleading. You see, galaxies are mostly empty space. Even though the Milky Way has hundreds of billions of stars, those stars are incredibly far apart. If you shrunk the sun down to the size of a grain of sand, the nearest star would be about 4 miles away. That is how much empty space there is between stars. And because of all that empty space, when two galaxies pass through each other, the stars almost never actually hit each other. Think about it this way. Imagine two swarms of bees flying toward each other. Each swarm has billions of bees, but the bees are spread out over such a huge area that when the swarms pass through each other, most of the bees do not even come close to touching. They just fly right past each other. That is kind of what will happen when Andromeda and the Milky Way collide. The stars will mostly just pass by each other in the night. But that doesn't mean nothing will happen. Far from it. The collision will completely change both galaxies. The beautiful spiral arms that make the Milky Way and Andromeda so striking will be torn apart. Stars will be thrown into new orbits. Some will be flung out into the darkness between galaxies, never to return. Others will be pulled toward the center, where something even more dramatic awaits. At the heart of both galaxies, there are supermassive black holes. These are not ordinary black holes. These are monsters. The black hole at the center of the Milky Way is called Sagittarius A star. It weighs about 4 million times more than our Sun, and it sits there in the middle of our galaxy, affecting everything around it with its massive gravity. Andromeda has its own supermassive black hole, and it is even bigger than ours. When the two galaxies merge, these two black holes will eventually find each other. They will circle around each other, getting closer and closer. And after millions of years of this gravitational dance, they will merge into one enormous black hole at the center of the new combined galaxy. But we are getting ahead of ourselves. Before we can talk about the end of this story, we need to understand the beginning. We need to know how scientists figured out that this collision is coming. We need to understand the timeline, and we need to explore what will happen at each stage of this cosmic merger. The story of how we discovered Andromeda's approach is a story of human curiosity and clever science. For a long time, people thought Andromeda was just a fuzzy patch of light in the night sky. They called it a nebula, which means cloud. They had no idea it was actually an entire galaxy, filled with hundreds of billions of stars located millions of light years away. That changed in the early 1900s when astronomers developed better telescopes and better ways to measure distances in space. They realized that Andromeda was not a cloud inside our galaxy. It was a separate galaxy entirely, and it was the closest large galaxy to our own. But knowing that Andromeda exists is one thing. Knowing that it is heading toward us is another. To figure that out, scientists had to measure something called blue shift. Here is how that works. When an object in space is moving toward you, the light it gives off gets compressed. This makes the light look slightly more blue than it would otherwise. When an object is moving away from you, the light gets stretched out. This makes it look slightly more red. By looking at the light from Andromeda and measuring how blue it appeared, scientists could tell that it was moving toward us, and not just moving toward us slowly. Andromeda is approaching at tremendous speed. It is covering about 250 miles every single second. That is fast enough to travel from New York to Los Angeles in about 10 seconds. And it has been traveling at that speed for billions of years. But even at that incredible velocity, the collision is still a long way off. Remember, Andromeda is currently about 2.5 million light years away. A light year is the distance that light travels in 1 year, moving at 186,000 miles per second. That is almost 6 trillion miles. And Andromeda is 2.5 million of those away. So when will the collision actually happen? Scientists have calculated that the two galaxies will have their first close encounter in about 4.5 billion years. That is roughly the same amount of time that has passed since the Earth first formed. In other words, the Earth is about as old as the time we have left before the collision begins. That first encounter will not be the end of the story, though. When two galaxies pass close to each other, gravity makes them swing around and come back for another pass, then another, and another. The whole process of merging will take about 2 billion years from start to finish. So while the first encounter happens in 4.5 billion years, the final merger will not be complete until about 6 billion years from now. During that time, the two galaxies will pass through each other multiple times. Each pass will disrupt their shapes more and more. The spiral arms will be stretched and torn. Long streamers of stars will be pulled out into space. The night sky, if anyone is around to see it, will put on a show unlike anything we can imagine today. Let us take a closer look at what scientists expect to happen during each phase of this cosmic event. Understanding the timeline helps us appreciate just how different this collision is from the crashes we experience in everyday life. Right now, in the present day, Andromeda appears as a faint smudge of light in the night sky. You can see it with your naked eye if you know where to look, and the conditions are right. It appears about 6 times wider than the full moon, though most of that width is too faint for our eyes to detect. What we see is just the bright central core. But even though it looks small and faint, Andromeda is actually larger than the Milky Way. It contains about 1 trillion stars, compared to our 200 to 400 billion. Its diameter is about 220,000 light years, while the Milky Way spans only about 100,000 light years. So in this collision, we are actually the smaller partner. Over the next few billion years, Andromeda will slowly grow larger in our sky. At first, the change will be too small to notice. Even after 1 million years, the difference will be tiny. But as we get closer to the collision, the change will become more and more obvious. About 3 billion years from now, Andromeda will start to look noticeably larger. Instead of a faint smudge, it will be a clear spiral visible to the naked eye. Its arms will stretch across the sky like great rivers of light, and it will keep getting bigger. By 4 billion years from now, just 500 million years before the first encounter, Andromeda will dominate the night sky. It will look massive, stretching from horizon to horizon. The spiral structure will be clearly visible, with dark dust lanes and bright star clusters dotting its arms. It will be the most spectacular sight in the heavens. Then the collision begins. The first pass will happen around 4.5 billion years from now. As the two galaxies approach each other, their gravitational fields will start to interact. The outer edges will feel the pull first. Stars that were peacefully orbiting in the outer arms will have their paths disrupted. Some will speed up, others will slow down. The orderly spiral structure will begin to break down. During the first pass, the two galaxies will not actually merge. They will sweep past each other, their cores passing within perhaps 50,000 light years of each other. That might sound close, but remember, the Milky Way alone is 100,000 light years across, so the cores will pass by without directly touching, but the gravitational effects will be enormous. Imagine taking 2 carefully arranged piles of sand and dragging magnets through them. The sand would be scattered everywhere, pulled this way and that by the invisible magnetic force. That is similar to what will happen to the stars in both galaxies during that first pass. Long tidal tails of stars will be pulled out from both galaxies. These are streamers of stars that get stretched out by gravity as the galaxies pass by each other. Some of these tails can extend for hundreds of thousands of light years into intergalactic space. They are some of the most beautiful structures in the universe, ribbons of light stretching across the darkness. After the first pass, the two galaxies will swing around each other and come back for a second encounter. This is because gravity is still pulling them together. Even though they pass by each other, they did not have enough speed to escape each other's pull. So back they come. The second pass will be even more disruptive than the first. By this point, the spiral arms of both galaxies will be badly damaged. They will no longer look like the neat, orderly spirals we see in pictures. Instead, they will look chaotic and messy, with stars scattered in all directions. More tidal tails will form. More stars will be flung out into intergalactic space, and the cores of the two galaxies will get closer together. The gravitational interaction will slow them down relative to each other, setting them up for the final merger. Over the next billion years or so, the two galaxies will continue to orbit around each other, getting closer and closer with each pass. Each orbit will take hundreds of millions of years to complete, and each time they pass by, they will lose a little more of their original shape. Eventually, after several passes, the two galaxies will merge completely. The cores will combine. The scattered stars will settle into new orbits around the combined center, and a new galaxy will be born from the union of the Milky Way and Andromeda. Scientists have already given this future galaxy a name. They call it Milkomeda. Some call it Milkdromeda. Either way, it is the galaxy that will exist billions of years from now, long after the Milky Way as we know it is gone. But what kind of galaxy will Milkomeda be? Will it look anything like the beautiful spirals that merged to create it? The answer, unfortunately, is no. Milkomeda will be an elliptical galaxy, not a spiral one. Elliptical galaxies are different from spirals in many ways. While spiral galaxies like the Milky Way have a flat disk shape with arms swirling around a central bulge, elliptical galaxies are more like giant balls of stars. They do not have the dramatic spiral arms. They do not have the flat disk. They are just enormous collections of stars arranged in a roughly spherical or oval shape. This happens because of how the merger process works. The spiral arms depend on stars orbiting in an orderly fashion, all moving in roughly the same direction around the galaxy center. When two galaxies merge, all that order gets disrupted. Stars end up orbiting in all different directions. The organized structure that creates spiral arms is destroyed and cannot reform. So Milkomeda will be a large, round, reddish galaxy. It will still have hundreds of billions of stars, but it will not have the elegant spiral shape that makes the Milky Way and Andromeda so beautiful today. Now, you might be wondering about something important. What about us? What happens to our solar system? What happens to Earth? Will we survive the collision? These are natural questions to ask. After all, we live here. We care about what happens to our home. And the good news is that the collision between Andromeda and the Milky Way probably will not destroy the Earth, at least not directly. Remember what we said earlier about how stars rarely actually hit each other during galaxy collisions? That applies to our Sun too. The chances of another star hitting our Sun or passing close enough to disrupt the solar system are very, very small. There is just too much empty space between stars for collisions to be likely. But that does not mean the solar system will come through completely unchanged. There are three main possibilities for what could happen to our cosmic neighborhood during and after the merger. The first possibility is that the solar system will remain in the new galaxy, orbiting the combined center of Milkomeda, much like it orbits the center of the Milky Way today. This is actually the most likely outcome. Most stars in both galaxies will end up as part of the merged galaxy, just in new orbits. The second possibility is more dramatic. The gravitational interactions during the merger could fling the solar system out into intergalactic space. We could become what scientists call a rogue star, wandering through the darkness between galaxies, no longer bound to any galactic home. This might sound scary, but it would not necessarily be a disaster. The sun would still shine, the planets would still orbit. Life, if it still exists, could continue. We would just be very, very alone, drifting through the emptiness between galaxies, with no nearby stars to call neighbors. The third possibility is that the solar system's orbit could be changed dramatically. We might end up much closer to the galactic center, where stars are packed more tightly together. Or we might end up in the outer reaches, where the night sky would show far fewer stars than we see today. But here is the thing. By the time the collision happens, the Earth probably will not be a good place for life anymore anyway. The sun is slowly getting brighter over time. In about 1 billion years, it will be bright enough to boil away the Earth's oceans. In about 5 billion years, the sun will run out of hydrogen fuel and start expanding into a red giant star. It will grow so large that it might actually swallow the Earth. So while the galaxy collision will not directly destroy our planet, the sun's natural evolution probably will. Unless future humans find a way to move to another star system, Earth will become uninhabitable long before Milky finishes forming. This might seem depressing, but there is another way to look at it. The collision between Andromeda and the Milky Way is not really an ending. It is a transformation. It is a new beginning. And in many ways, it is a beautiful example of how the universe constantly renews itself. When the two galaxies merge, something amazing will happen. The shock waves and gravitational disruptions will compress huge clouds of gas and dust. This compression will trigger a burst of new star formation. For a while, Milky will light up with thousands of new stars being born every year. Astronomers call this a starburst. It is like a fireworks show on a galactic scale. New stars of all sizes will ignite, flooding the galaxy with light. Some of these new stars will be massive and blue, burning hot and bright. Others will be small and red, destined to shine steadily for trillions of years. Around some of these new stars, planets will form. Rocky worlds like Earth, gas giants like Jupiter, icy moons like Europa. The raw materials for life created in the hearts of ancient stars will be recycled into new worlds with new possibilities. In this sense, the galaxy collision is not destruction. It is creation. It is the universe taking the old and making something new. The spiral beauty of the Milky Way will be lost, but something else will take its place. And that something could be home to forms of life we cannot even imagine. Let us turn our attention now to what is perhaps the most dramatic part of the entire collision: the merger of the supermassive black holes at the centers of both galaxies. This is where the physics gets truly extreme. As we mentioned earlier, both the Milky Way and Andromeda have supermassive black holes at their centers. The Milky Way's black hole, Sagittarius A star, has a mass about 4 million times that of our Sun. Andromeda's black hole is even bigger, with a mass over 100 million times that of our Sun. During the galaxy merger, these two black holes will eventually find each other, but it will take time. At first, as the galaxies begin to interact, the black holes will remain in the cores of their respective galaxies. They will be surrounded by dense clusters of stars and clouds of gas. As the merger progresses and the two cores get closer, the black holes will start to orbit around the combined center of mass. They will be separated by thousands of light years at first, each with its own retinue of stars and gas. Over millions of years, gravitational friction will bring them closer together. As they move through the sea of stars in the combined core, they will gradually lose energy. Each encounter with a passing star will slow them down slightly. Little by little, their orbits will shrink. Eventually, the two black holes will come within a few light years of each other. At this point, the stars that had been orbiting with them will be largely ejected. The black holes will form what astronomers call a binary, two massive objects orbiting around their common center of mass. This binary will continue to shrink, but more slowly now. With most of the nearby stars already ejected, there is less gravitational friction to drain their orbital energy. The black holes might spend billions of years in this close binary state, slowly spiraling inward. Finally, when they get close enough, a new effect takes over. As the black holes orbit each other at high speed, they will create ripples in the fabric of space and time itself. These ripples are called gravitational waves, and they carry energy away from the system. Albert Einstein predicted the existence of gravitational waves over 100 years ago as part of his theory of general relativity. For a long time, they were impossible to detect, but in recent years, scientists have built incredibly sensitive instruments that can pick up these tiny ripples in space-time when massive objects merge. When the two supermassive black holes in Milky finally merge, they will release an enormous burst of gravitational waves. This will be one of the most energetic events in the history of the local universe. The ripples will spread out at the speed of light, carrying news of the merger across the cosmos. The final merger will happen quickly, at least on cosmic timescales. In the last moments, the black holes will be orbiting each other at a significant fraction of the speed of light. They will complete hundreds of orbits in just seconds. Then they will come together, merging into a single, even more massive black hole. This new black hole will be a monster. It will have a mass somewhere around 150 to 200 million times that of our Sun. It will sit at the center of Milky, the gravitational anchor around which all the stars in the new galaxy orbit. The merger itself will be violent. As the two black holes combine, they will release energy equivalent to the mass of millions of suns, all converted directly into gravitational wave energy. This is the most efficient energy release process known to physics, far more efficient than nuclear fusion or even matter-antimatter annihilation. Some of this energy might also be released as electromagnetic radiation. Gas and dust falling toward the merging black holes could heat up to extreme temperatures, producing X-rays and gamma rays. If there happens to be a lot of gas available, the merger could briefly turn the core of Milky into something resembling a quasar, one of the brightest objects in the universe. A quasar is an active galactic nucleus powered by a supermassive black hole actively consuming large amounts of matter. The matter forms a disk around the black hole, spiraling inward and heating up to incredible temperatures as it does. This hot disk can outshine all the stars in the galaxy combined, creating a beacon visible across billions of light years. Not all galaxy mergers create quasars. It depends on how much gas is available and how it falls toward the central black hole. The merger of the Milky Way and Andromeda might or might not produce a quasar phase. Scientists are not sure, but even if it does not create a full quasar, the central black hole will likely go through a period of increased activity as it settles into its new configuration. After the merger is complete, the combined black hole will quiet down. Without fresh fuel falling into it, it will become dormant, just like Sagittarius A star is today. It will sit at the center of Milky, invisible but incredibly massive, shaping the orbits of billions of stars through its immense gravity. Now let us zoom out and think about what all of this means in the bigger picture of cosmic history. The collision between Andromeda and the Milky Way is dramatic and fascinating, but it is not unique. Galaxy mergers happen all the time throughout the universe. They are a fundamental part of how galaxies grow and evolve. When the universe was younger, galaxies were smaller and more numerous. Over billions of years, they have been coming together through collisions and mergers. Small galaxies combine to form medium-sized galaxies. Medium galaxies merge to form large galaxies. The Milky Way itself has grown by absorbing smaller dwarf galaxies throughout its history. In fact, the Milky Way is currently in the process of absorbing several dwarf galaxies right now. The most famous is the Sagittarius Dwarf Elliptical Galaxy, which is being stretched and torn apart by the Milky Way's gravity. Its stars are being absorbed into our galaxy, adding to the Milky Way's total mass. There are other dwarf galaxies in our neighborhood too. The Large and Small Magellanic Clouds are two irregular dwarf galaxies that orbit the Milky Way. Eventually, they will likely be absorbed as well. These are small mergers compared to what will happen with Andromeda, but they are mergers nonetheless. The collision with Andromeda will be special because it involves two large, roughly equal-sized galaxies. This is called a major merger. Major mergers are more dramatic than minor mergers because both galaxies are significantly disrupted. The resulting galaxy is very different from either of the original ones. After Milky forms, it will probably not have any more major mergers for a very long time. The nearest large galaxy after Andromeda is the Triangulum Galaxy, also known as M33. It is only about 3 million light-years away, not much farther than Andromeda. But it is much smaller, with only about 40 billion stars compared to the Milky Way's 200 to 400 billion and Andromeda's trillion. Triangulum might actually participate in the Andromeda-Milky Way collision. Computer simulations suggest it could either merge with the Milky Galaxy or be flung out into intergalactic space by the gravitational interactions. Either way, after these mergers are complete, there will not be any more large galaxies nearby for Milky to merge with. This is because the universe is expanding. Everything in space is moving apart from everything else. While gravity can overcome this expansion on small scales, pulling galaxies like the Milky Way and Andromeda together, it cannot overcome the expansion across larger distances. The nearest large galaxy cluster to our local group is the Virgo cluster, about 50 million light-years away. Gravity is not strong enough to pull us toward Virgo. In fact, the space between us and the Virgo cluster is expanding, carrying us farther apart over time. Milky will remain isolated, with only its satellite dwarf galaxies for company. Billions of years from now, long after Milky has formed and settled into its final shape, the universe will look very different. The expansion of space will have carried all other galaxy clusters beyond our observable horizon. From Milky there will be no other galaxies visible in the sky, just darkness, extending forever in all directions. This is the far future of the universe, a time when each galaxy cluster, or in our case each merged supergalaxy, will be alone in an island of space surrounded by an ever-expanding void. The night sky from a planet in Milky trillions of years from now, will show only the stars of that one galaxy, no other galaxies, no distant lights from other cosmic islands, just the stars of Milky and the infinite darkness beyond. It is a lonely vision of the future, but it is also beautiful in its own way. Even in that distant time, stars will still shine, planets will still orbit, and perhaps life will still exist, wondering about the nature of the universe, just as we do today. But let us return to the more immediate future. If you can call 4.5 billion years immediate, let us think more carefully about what the collision will look like for any observers who happen to be around to see it. As we mentioned, the Milky Way and Andromeda are both spiral galaxies. From Earth, we see the Milky Way as a band of light across the night sky because we are inside it, looking along the plane of the disk. If we could travel outside our galaxy and look back at it, we would see the same kind of beautiful spiral structure that we see when we look at Andromeda. As the collision approaches, the night sky will change dramatically. Andromeda will grow from a faint smudge to a dominant presence. At first, it will look like a separate object, a distinct spiral floating among our stars. But as the two galaxies begin to interact, their shapes will start to change. The outer arms of both galaxies will be the first to feel the gravitational effects. Stars on the edges will be pulled toward the approaching galaxy. Long streamers will begin to form, reaching out like arms across the void. The neat spiral pattern will start to break down, replaced by something more chaotic and dramatic. During the first pass, observers on Earth, if any could exist at that time, would see an incredible sight. The sky would be filled with light from two intermingled galaxies. Stars from Andromeda would be mixed with stars from the Milky Way. Great arcs of light would stretch from horizon to horizon, marking the tidal tails being pulled out by gravity. The collision would happen in slow motion by human standards. Even though the galaxies are moving at hundreds of miles per second relative to each other, the distances are so vast that the changes would take millions of years to become obvious. But over geological time, the transformation would be breathtaking. New stars would be forming everywhere. The compressed gas clouds would light up with stellar nurseries, regions where hundreds or thousands of new stars were being born at once. These regions would glow with the light of young, hot stars, adding bright blue patches to the complex patterns in the sky. Meanwhile, the old stars would continue to shine, their familiar light mixed with the new. Red giants, white dwarfs, pulsars, and all the other stellar types would continue their lives, largely unaffected by the chaos around them. Stars are too small and too far apart for the collision to disrupt them directly. The gravitational disruptions would be the main visible effect. Stars would not explode or collide, but their paths through space would change. Some would be flung into highly elongated orbits, swooping close to the galactic center and then far out into the halo. Others would be ejected entirely, becoming rogues wandering through intergalactic space. After the first pass, the two galaxy cores would swing away from each other, only to be pulled back for another encounter. The sky would show the evidence of this ongoing dance, with great loops and streams of stars marking the gravitational interactions. It would be like watching two drops of water merge in slow motion, each pulling on the other, distorting and stretching before finally combining. The final merger would take place over hundreds of millions of years. The two cores, each home to a supermassive black hole, would spiral toward each other. The surrounding stars would settle into new orbits around the combined center. The chaotic streams and tails would gradually be absorbed, their stars finding new homes in the structure of Milky. When it was all over, the night sky would look completely different. Instead of the band of the Milky Way, observers would see the glow of a giant elliptical galaxy surrounding them in all directions. The spiral arms would be gone, replaced by a more diffuse, spherical glow of starlight. It would be a sky without the clear landmarks we know today. No Orion, no Big Dipper, no Southern Cross. All those familiar patterns, created by accident from our particular viewpoint within the Milky Way, would be scrambled and lost. New patterns would emerge, but they would belong to a new age, a new galaxy, a new home for whatever beings might exist to see them. Let us spend some time now talking about the science behind these predictions. How do astronomers know what will happen? How can they predict events billions of years in the future with any confidence? The answer lies in computer simulations. Modern astronomers use powerful computers to model the behavior of galaxies. They create virtual galaxies with billions of particles, each representing a clump of stars or dark matter. Then they let physics take over, calculating how gravity pulls these particles together and moves them through space. These simulations have become incredibly sophisticated. They can reproduce the shapes and behaviors of real galaxies with impressive accuracy. When astronomers simulate two spiral galaxies colliding, the results match what we see when we observe actual galaxy collisions happening elsewhere in the universe. And we have observed many such collisions. The universe is full of galaxies in various stages of merging. Some are just beginning to interact, with their spiral arms starting to distort. Others are in the middle of the process, showing the characteristic tidal tails and disturbed structures. Still others have finished merging and now appear as elliptical galaxies. By studying these other collisions, astronomers can check their simulations against reality. The agreement is remarkably good. The same physics that governs those distant mergers will govern the collision between our galaxy and Andromeda. One famous example of an ongoing merger is the Antennae galaxies, located about 45 million light-years away. These two galaxies are in the middle of colliding, and they show many of the features we expect to see when the Milky Way and Andromeda merge. Long tidal tails stretch out from the central region. The spiral structure is badly disrupted, and intense starbursts are occurring where gas clouds have been compressed. Another example is the Mice galaxies, named for their long tail-like tidal streams. These galaxies are also mid-collision, showing how gravity stretches and distorts the shapes of merging galaxies. Closer to home, we can see the effects of past and ongoing minor mergers on the Milky Way itself. The Sagittarius dwarf galaxy has left trails of stars as it has been torn apart by our galaxy's gravity. These streams help astronomers understand how mergers work and improve their simulations. For the specific case of the Milky Way and Andromeda, astronomers have run many detailed simulations. They input the current positions, velocities, and masses of both galaxies, including estimates for the dark matter halos. Then they let the simulation run forward in time, watching what happens. The results are consistent. The galaxies will collide in about 4.5 billion years. They will undergo several passes before merging completely. The final product will be a large elliptical galaxy, and the whole process will take about 2 billion years from first encounter to final merger. There is some uncertainty in these predictions, of course. We do not know the exact masses of the dark matter halos. We do not know the precise sideways velocity of Andromeda, which affects exactly how the collision plays out. Different assumptions lead to somewhat different outcomes, but the general picture is robust. The Milky Way and Andromeda are gravitationally bound to each other. They will collide. They will merge. The only questions are about the exact details and timeline. Recent observations from the Gaia Space Telescope have helped refine our predictions. Gaia has measured the positions and motions of over 1 billion stars in the Milky Way with unprecedented precision. This allows astronomers to better understand the structure and rotation of our galaxy, which improves the simulations. Gaia has also measured the motion of stars in the Milky Way's halo, and in nearby dwarf galaxies. This gives clues about the distribution of dark matter, which is crucial for predicting how the Andromeda collision will unfold. The more data we collect, the better our predictions become. Future telescopes and missions will continue to refine our understanding. By the time the collision happens, humanity will have had billions of years to prepare. Whether anyone will be around to care is another question. Speaking of preparation, let us think about what future civilizations might do as the collision approaches. If intelligent life still exists in the Milky Way billions of years from now, how might they respond to the coming merger? One thing to understand is that the collision itself is not really a threat in the traditional sense. As we have discussed, stars almost never actually collide during galaxy mergers. The danger is not from direct impacts, but from gravitational disruptions that could destabilize planetary orbits. A sufficiently advanced civilization might be able to predict which stellar systems are at risk and take action. They could move to a new star system if their original one becomes unstable. They could build habitats in interstellar space, independent of any particular star. They could even try to influence the orbits of stars to avoid dangerous encounters. Of course, this kind of civilization building is far beyond our current abilities. We cannot even visit other planets in our own solar system easily, let alone travel to other stars. But billions of years is a long time. Technologies that seem like magic to us today might be routine for our distant descendants. There is also the possibility that no one will be around to worry about the collision. Human civilization is only a few thousand years old. Homo sapiens as a species is only a few 100,000 years old. The timescales involved in the galaxy collision are millions of times longer than human history. It is hard to predict what will happen to life on Earth, let alone intelligent life, over such vast stretches of time. Evolution will continue. Species will rise and fall. Mass extinctions will happen. The Earth itself will change dramatically as the Sun evolves. By the time Andromeda arrives, Earth may have been uninhabitable for billions of years. Life, if it exists anywhere in the galaxy, might have spread to other star systems. Or it might have died out entirely. We simply cannot know. What we can know is that the universe will continue regardless. The collision will happen whether anyone is watching or not. Galaxies have been merging since galaxies first formed, billions of years before the Earth existed. They will continue merging long after any trace of our civilization is gone. There is something humbling about this perspective. We go about our daily lives, worrying about things that seem important in the moment. But the universe operates on scales that make human concerns seem trivial. A galaxy collision that will happen in 4 billion years. A merger that will take 2 billion years to complete. A timeline that stretches beyond any human comprehension. And yet, there is also something inspiring about it. We are small, yes. Our lives are short, but we have the ability to understand processes that unfold over billions of years. We can peer across millions of light years and deduce what will happen in the distant future. We can run simulations and make predictions. We can grasp the workings of the cosmos. That is remarkable. In all the universe, so far as we know, only on this one small planet has matter organized itself to contemplate such questions. Only here, on Earth, have beings emerged who can look at the faint smudge of Andromeda in the night sky and understand that it foretells a transformation billions of years hence. Whether human beings or our descendants will exist when that transformation happens, we cannot say. But the fact that we can think about it at all, that we can understand it and wonder at it, is a kind of triumph. We are the universe becoming aware of itself, if only for a brief moment in cosmic time. Let us now turn to some questions that people often ask about the Andromeda collision. These are the things that puzzle and fascinate us as we try to wrap our minds around such an extraordinary event. One common question is whether the collision could happen sooner than predicted. What if the scientists are wrong? What if Andromeda is moving faster than we think? The answer is that while there is some uncertainty in the predictions, the collision cannot happen significantly sooner than expected. We can measure Andromeda's distance quite precisely using several different methods. We can also measure its velocity toward us with good accuracy. These measurements constrain when the collision can occur. Even if the velocity was somewhat higher than estimated, the collision would only happen slightly sooner. We are talking about the difference between 4.5 billion years and maybe 4 billion years. Either way, it is far in the future, long after any recognizable form of current life would still exist. Another question people ask is whether we could prevent the collision somehow. Could we use rockets or nuclear weapons or some other technology to push Andromeda away? The answer is definitely no. The masses involved are simply too large and the distances too great. Andromeda has the mass of about 1 trillion suns. No technology we can imagine would be capable of affecting the motion of something that massive. It would be like trying to stop a freight train by throwing pebbles at it. And even if we could somehow generate enough force, where would we apply it? Andromeda is spread across hundreds of thousands of light years. There is no single point to push on. You would have to somehow affect the motion of 1 trillion stars and their associated dark matter. It is completely impossible. Some people ask whether the collision could affect other galaxies in our local group. The local group is the collection of galaxies that are gravitationally bound together in our cosmic neighborhood. Besides the Milky Way and Andromeda, it includes several dozen smaller galaxies. The answer is that many of these smaller galaxies will indeed be affected. Some may be absorbed into Milky, along with the main galaxies. Others may be flung out into intergalactic space by the gravitational chaos. The Triangulum galaxy in particular might merge with Milky or be ejected. After Milky forms, it will probably still have some dwarf galaxy companions, just as the Milky Way does today. But the configuration will be different, and some current members of the local group will be gone. Another frequent question is about what the night sky will look like during and after the collision. We have discussed this somewhat, but let us add more detail. During the collision, the night sky will be much brighter and more dramatic than it is today. There will be more stars visible because of the starburst activity. The familiar constellations will be gradually disrupted as the Milky Way's structure changes. Eventually, observers will see themselves embedded in a giant elliptical glow rather than a band of light. One particularly striking phase will come when Andromeda first starts to dominate the sky. Imagine looking up and seeing a spiral galaxy stretched across the heavens, its arms visible to the naked eye, its central bulge a brilliant core of light. It will be like nothing any human has ever seen. After the merger is complete, the sky will be more uniform, but also more isolated. Without the spiral arm structure, there will be fewer dense star clouds creating distinctive patterns. The night sky will glow with a diffuse light from the billions of stars in all directions, but there will also be no other galaxies easily visible, as the expansion of space will have carried them beyond what can be seen. People sometimes ask about the black hole merger specifically. Will we be able to see it? Will it be dangerous? The gravitational wave burst from the black hole merger will be detectable from anywhere in the universe with the right instruments. but it will not be dangerous. Gravitational waves carry energy, but they do not interact strongly with matter. A gravitational wave passes through you every time two black holes merge somewhere in the universe. You never notice it, because the effect is so tiny. The black holes themselves could be dangerous if you got too close. The region near a supermassive black hole is an extremely hostile environment with intense gravity, radiation, and energetic particle jets. But these effects are localized. At the distance of our solar system from the galactic center, the black hole merger will have no significant effect. There might be some electromagnetic radiation associated with the merger, as we discussed earlier. If gas is falling into the merging black holes, it could produce X-rays and gamma rays. But again, at interstellar distances, this radiation would not be dangerous. Space is vast, and radiation intensity decreases with the square of the distance. Another question that comes up is whether the collision could create any exotic phenomena like wormholes or time travel opportunities. As far as we know, no. General relativity does allow for the theoretical existence of wormholes, which are shortcuts through space-time. But there is no evidence that real wormholes exist, and even if they did, we have no reason to think a galaxy collision would create one. The physics of the collision, while extreme by everyday standards, is actually quite straightforward by cosmic standards. Gravity pulls things together, stars move in response, gas gets compressed, black holes merge. All of this follows the ordinary laws of physics as we understand them. No exotic new physics is expected. Let us spend some time considering what we have learned and what it tells us about the nature of the universe. The collision between the Milky Way and Andromeda is just one example of a process that has been shaping the cosmos since the beginning. Gravity brings matter together. Small structures combine to form larger structures. Simple things become complex things. In the very early universe, shortly after the Big Bang, matter was spread almost uniformly through space. There were slight variations in density, tiny ripples in the fabric of reality. But gravity amplified these ripples over time. Regions that were slightly denser pulled in more matter, becoming even denser. Eventually, these regions collapsed to form the first stars and galaxies. Those early galaxies were small and chaotic. They did not look like the beautiful spirals we see today, but through mergers and collisions they grew. Small galaxies combined to form medium galaxies. Medium galaxies merged to form large galaxies. The process has been ongoing for over 13 billion years. The Milky Way is itself a product of this history. It has absorbed many smaller galaxies over its lifetime. The stars in its halo, the old stars that orbit above and below the main disk, include many that were once part of other galaxies. They were absorbed long ago and are now part of our galactic family. When the Milky Way merges with Andromeda, it will be continuing this ancient process. The result will be a larger galaxy, formed from the combination of two smaller ones. And eventually, that larger galaxy might merge with others. Though given the expansion of the universe, large-scale mergers will become increasingly rare in the far future. This pattern of growth through combination is seen throughout nature. Atoms combine to form molecules. Molecules combine to form cells. Cells combine to form organisms. In a similar way, stars combine to form clusters. Clusters combine to form galaxies. And galaxies combine to form larger galaxies. There seems to be a tendency in the universe toward complexity, toward the building of larger and more intricate structures from simpler components. The galaxy collision is just one manifestation of this tendency, played out on the larger scales. Of course, the building process is not infinite. Eventually, the expansion of the universe will overcome gravity on large scales. Galaxy clusters will drift apart, never to meet again. The merging process will slow and stop. Each island of galaxies will be alone in an ever-expanding void. But even this is not the end. Within each isolated galaxy cluster, stars will continue to shine for trillions of years. New stars will form from gas and dust. Old stars will die and return their material to the cosmos. The cycle of stellar birth and death will continue long after the last galaxy mergers have occurred. Eventually, even the stars will run out. The universe will enter an era of darkness, lit only by the faint glow of white dwarfs cooling to invisibility and the occasional flash of stellar remnants colliding. Black holes will slowly evaporate over timescales that dwarf even the ages of galaxies. And eventually, only empty, cold space will remain. But that is trillions upon trillions of years in the future. For now, and for a very long time to come, the universe is full of light and activity. Stars are being born, planets are forming, galaxies are growing and merging, and on at least one small world, intelligent beings are looking up at the night sky and trying to understand it all. The collision between Andromeda and the Milky Way will be one chapter in this cosmic story. It will not be the last chapter, but it will be a significant one. A transformation that will reshape our corner of the universe for billions of years. If you are watching this from Earth today, know that you are witnessing a beautiful moment in cosmic history. The Milky Way, as we know it, with its elegant spiral arms and its familiar band across the night sky, will not last forever. But it exists now, and you can see it, and you can understand what it means. Go outside on a clear night. Look up at the stars. Find the band of the Milky Way stretching across the darkness. And if you can, find the faint smudge of Andromeda, the galaxy that is slowly making its way toward us. When you look at that smudge, you are seeing light that left Andromeda 2.5 million years ago. That light has been traveling through the void, all this time, racing toward us at the speed of light. And during all that time, Andromeda itself has been moving toward us too, carried by the gravity that binds our two galaxies together. The collision is coming, but not yet. Not for billions of years. For now, we can simply marvel at the fact that we know about it. We can appreciate the beauty of our spiral galaxy and the drama of the transformation to come. We can feel connected to a cosmos that operates on scales beyond human comprehension, yet is somehow still comprehensible to human minds. That is the wonder of astronomy. It shows us our place in the universe, which is both insignificant and extraordinary. We are made of star stuff, born on a small planet orbiting an ordinary star in one arm of an ordinary galaxy. But we can understand the forces that will reshape that galaxy billions of years from now. We are the universe looking back at itself, trying to figure out its own story. The Milky Way and Andromeda are destined to merge. When they do, something new will be born. Milky will rise from the union, a vast elliptical galaxy with hundreds of billions of stars. Some of those stars will have planets. Some of those planets might have life. And perhaps, in the far distant future, beings on those worlds will look up at their night sky and wonder about the history of their cosmic home. They will be the inheritors of a legacy that stretches back billions of years to a time when two spiral galaxies began their slow dance toward merger. A dance that started before the Earth, existed and will continue long after it is gone. This is the final hour that is coming. Not an hour on a clock, but an epoch in cosmic time. a moment of transformation when two great galaxies become one. It is both an ending and a beginning, both a destruction and a creation, both a loss and a gain. And it is real, not science fiction, not speculation, real physics playing out on a real timescale in the real universe that we inhabit. As we wrap up our journey through this cosmic future, let us remember what we have learned. The Milky Way and Andromeda are approaching each other at about 250 miles per second, pulled together by gravity and dark matter. They will have their first close encounter in about 4.5 billion years. The collision will unfold over 2 billion years as the galaxies pass through each other multiple times before finally merging. The beautiful spiral arms of both galaxies will be destroyed, replaced by the smoother structure of an elliptical galaxy called Milky. The supermassive black holes at the centers of both galaxies will eventually merge, creating an even larger black hole at the heart of the new galaxy. And through it all, new stars will be born, even as old structures are torn apart. If you have made it this far, thank you for joining me on this journey through billions of years of cosmic history. If you found this exploration fascinating, please consider subscribing to the channel and hitting the notification bell so you do not miss future videos about the wonders of the universe. We have so much more to explore together, from the smallest particles to the largest structures in the cosmos. The universe is full of stories waiting to be told. The collision between Andromeda and the Milky Way is one of the greatest stories of all, a tale of transformation on a scale almost beyond imagination. Thank you for being part of the audience for this cosmic drama, even if the climax is still billions of years away. Look up at the stars tonight. Remember that you are part of something vast and ancient and ongoing. And know that even as you stand there, Andromeda is making its way toward us, one moment at a time, bringing the future ever closer. Until next time, keep wondering, keep exploring, and keep looking up. Now, let us delve even deeper into some of the most fascinating aspects of this cosmic collision. We have covered the basics, but there is so much more to explore about what makes this event so remarkable in the history of our local universe. Consider for a moment the concept of cosmic time. We humans measure our lives in decades. We measure history in centuries or millennia. But the universe operates on timescales that make human history look like the blink of an eye. The collision between Andromeda and the Milky Way will take place over a span of time so vast that our brains can barely process it. 4.5 billion years. Say it out loud and let it sink in. That is the time we have before the first close encounter. To put it in perspective, 4.5 billion years ago, the Earth was just forming. The solar system was a disk of gas and dust surrounding a young sun. The first rocks were beginning to cool. Life had not yet appeared. Everything that has ever happened on Earth, from the formation of the first continents to the evolution of life, from the age of dinosaurs to the rise of human civilization, all of that has taken place in roughly the same amount of time that remains before the collision. We are, in a sense, at the halfway point. Half the time since Earth formed has passed. Half the time until the collision remains. This perspective can be both humbling and awe-inspiring. It reminds us that our existence is a tiny sliver of cosmic history, but it also reminds us that we are part of something much larger than ourselves, a universe with a history measured in billions of years and a future that stretches even further. Let us think more carefully about the physics of gravity and how it orchestrates this cosmic dance between galaxies. Gravity is the weakest of the four fundamental forces of nature, far weaker than electromagnetism or the nuclear forces. Yet it is gravity that shapes the largest structures in the universe. The reason gravity dominates on cosmic scales is that it always attracts, never repels. The other forces can both attract and repel, so their effects tend to cancel out over large distances. But gravity just keeps pulling, accumulating its effect as more and more mass is involved. The gravitational attraction between the Milky Way and Andromeda is the result of their combined mass, most of which is dark matter. Remember, the visible stars and gas in both galaxies make up only a small fraction of their total mass. The dark matter halos are much more massive, extending far beyond the visible disk of each galaxy. These dark matter halos are like invisible scaffolds that hold the galaxies together. Without dark matter, the stars would not orbit as fast as they do. The galaxies would be smaller and less tightly bound, and the gravitational attraction between them would be much weaker. It was actually the study of galaxy rotation that first revealed the existence of dark matter. In the 1970s, astronomer Vera Rubin measured how far stars were orbiting in various galaxies. She found that stars on the outer edges of galaxies were moving much faster than expected based on the visible mass alone. There had to be extra mass that we could not see, mass that was providing the extra gravity needed to keep those fast-moving stars in orbit. Since then, many other observations have confirmed the existence of dark matter. We can see its effects in the way galaxies cluster together. We can see it in the gravitational lensing caused by massive galaxy clusters, where the dark matter bends the light from more distant objects. We can even see its fingerprint in the cosmic microwave background, the faint glow left over from the early universe. All of this dark matter contributes to the gravitational pull between Andromeda and the Milky Way. In fact, most of the pull comes from the dark matter, not from the stars we can see. The collision is really a collision of dark matter halos, with the visible galaxies along for the ride. When the halos merge, they will combine into a single, larger halo. This process is called violent relaxation, not because it involves violence in the usual sense, but because the gravitational field changes so rapidly that stars and dark matter particles quickly forget their original orbits and settle into new ones. The end result is a well-mixed halo with a smooth distribution of dark matter surrounding the merged galaxy. The dark matter merger will actually happen faster than the merger of the visible galaxies. Dark matter does not interact with itself through any force except gravity. It passes through other dark matter without resistance, so the dark matter halos will interpenetrate and begin mixing almost immediately during the collision, while the stars take longer to settle into their new orbits. This is one of the things that makes galaxy collisions so different from everyday collisions. When two cars crash, the metal crumples and the cars come to a sudden stop. But when two galaxies collide, most of the matter just passes through. It is more like two clouds of fog drifting through each other than two solid objects crashing. The exception is the gas. While stars pass by each other without interacting, gas clouds can collide directly. When they do, they heat up and compress, triggering bursts of star formation. This is why merging galaxies often show intense starburst activity. The gas clouds are the only component that actually crashes in the traditional sense. The Milky Way and Andromeda both contain substantial amounts of gas, so we can expect significant star formation when they collide. New stars will light up the night sky, adding to the spectacle of the merger. Some of these stars will be massive and blue, burning hot, and bright, but living short lives. Others will be smaller and redder, less spectacular, but destined to shine for billions of years. The gas will also feed the supermassive black holes at the centers of both galaxies. As gas falls toward a black hole, it forms a disk that spirals inward. This disk can get extremely hot, radiating energy across the electromagnetic spectrum. If enough gas is available, the black hole can become what astronomers call an active galactic nucleus, outshining all the stars in the galaxy combined. Whether the Milky Way Andromeda merger will produce an active galactic nucleus is uncertain. It depends on how much gas is available and how it flows toward the black holes. Some simulations suggest there could be a period of quasar-like activity. Others suggest the black holes will remain relatively quiet. We will not know for sure until the merger actually happens, billions of years from now. Let us now consider what astronomers have learned by observing other galaxy mergers throughout the universe. Remember, we cannot watch the Milky Way Andromeda collision in real time because it will take billions of years to unfold. But we can observe many other collisions at various stages, providing snapshots of what the process looks like. One of the most studied examples is the system called NGC 4038 and NGC 4039, better known as the Antennae Galaxies. This pair is located about 45 million light-years away in the constellation Corvus. The two galaxies are in the middle of a major merger, with their cores separated by only about 30,000 light-years. The Antennae Galaxies show many of the features we expect to see during the Milky Way Andromeda collision. There are two long tidal tails extending from the system, formed as gravity pulled stars out from the original galaxies. These tails stretch for hundreds of thousands of light-years into space, giving the system its name because they look like the antennae of an insect. In the central region, where the two galaxies are overlapping, there is intense star formation. Infrared observations have revealed hundreds of young star clusters forming in the compressed gas clouds. Some of these clusters contain millions of stars, making them comparable to the globular clusters that orbit our own galaxy. The Antennae Galaxies are thought to be about 700 million years into their merger process. The first close encounter happened long ago, and the two cores have already completed several passes. In about 400 million years, the cores will merge completely, and the system will settle into an elliptical galaxy. Another interesting example is the Mice Galaxies, also known as NGC 4676. This pair got its name because the long tidal tails resemble the tails of mice. Like the antennae, the Mice Galaxies are in mid-collision, showing the dramatic effects of gravitational interaction. The Mice Galaxies are located about 300 million light-years away. They are at an earlier stage in their merger than the antennae, with their cores still well separated. The tidal tails are particularly prominent, showing how gravity can stretch and distort the shapes of colliding galaxies. Studies of the Mice Galaxies have helped astronomers understand how tidal tails form. As two galaxies approach each other, their gravitational fields create tides in each other, much like how the Moon creates tides in Earth's oceans. These tides can pull stars away from the main body of each galaxy, creating the long streamers of stars we see in the tidal tails. A more advanced merger can be seen in the system called NGC 7252, sometimes known as Atoms for Peace. This galaxy appears to be a single elliptical galaxy, but its unusual structure reveals that it formed from a recent merger. There are two faint tidal tails still visible, and the core shows signs of recent star formation activity. NGC 7252 is thought to be about 1 billion years past the final coalescence of its parent galaxies. It gives us a preview of what Milkomeda might look like after the Milky Way and Andromeda have finished merging. The spiral structure is gone, replaced by a smooth elliptical shape. The tidal tails are fading. The galaxy is settling into its new form. Even more ancient mergers can be identified by studying the stellar populations in elliptical galaxies. Many large ellipticals show evidence of multiple merger events in their past, with stars of different ages and chemical compositions mixed together. These stellar archaeology studies help astronomers reconstruct the merger history of galaxies throughout the universe. The Milky Way itself bears the scars of past mergers. In 2018, astronomers analyzed data from the Gaia Space Telescope and discovered evidence of a major merger that happened about 10 billion years ago. A dwarf galaxy, now called Gaia Enceladus, collided with the early Milky Way and was absorbed. The stars from Gaia Enceladus can still be identified today. They have distinctive chemical signatures and orbital properties that set them apart from stars that formed within the Milky Way itself. These stars now populate the inner halo of our galaxy, mixed with other halo stars, but still recognizable by their unique characteristics. This ancient merger helped shape the Milky Way into the galaxy we see today. It added mass and angular momentum. It may have triggered episodes of star formation. It contributed stars that are now spread throughout the halo. In a sense, the Milky Way is already a product of cosmic collision and merger. The upcoming merger with Andromeda will be much more dramatic than the Gaia Enceladus event. That was a minor merger where a small galaxy was absorbed by a larger one. The Andromeda collision will be a major merger, involving two galaxies of similar size. The effects will be correspondingly more dramatic. Let us now explore some of the more exotic phenomena that might occur during and after the galaxy collision. While we have focused mainly on stars and black holes, there are other interesting possibilities to consider. One question that astronomers have studied is whether the collision could affect habitability within the galaxies. Could the disruptions make it harder for life to exist? Or could they create new opportunities for life to arise? The answer is complicated. On one hand, the collision itself is unlikely to directly harm life on any particular planet. As we have discussed, stars rarely collide during galaxy mergers. Planets would continue to orbit their stars much as before. The night sky would look different, but the local conditions on a planet would not change dramatically. On the other hand, the collision could have indirect effects on habitability. The starburst triggered by the merger would produce many massive stars, and massive stars end their lives in supernova explosions. If the rate of supernova increases significantly, it could increase the radiation hazard in the galaxy. A supernova explosion within a few tens of light years of a planetary system could be dangerous. The radiation and cosmic rays from the explosion could damage the atmosphere and harm life on any planets nearby. If supernovae become more common during the merger, the probability of such close encounters would increase. However, even with increased supernova rates, the galaxy is a big place. The chance of any particular planetary system being affected by a nearby supernova is still quite small. Life throughout the galaxy would probably continue much as before, with occasional disruptions affecting some systems but not others. Another effect to consider is the change in the galactic environment. The Milky Way currently has a relatively quiet center, with our supermassive black hole not actively consuming much material. During the merger, the black hole might become more active, producing jets of high-energy particles and radiation. These jets could have effects throughout the galaxy. High-energy particles accelerated by the black hole could propagate outward, contributing to the cosmic ray background. Radiation from the active nucleus could potentially affect habitability in the inner regions of the galaxy. Those systems in the outer regions would likely be too far away to be significantly impacted. Perhaps the most interesting effect of the merger on habitability is the change in stellar density. In the merged elliptical galaxy, stars will be distributed more uniformly than in the current spiral structure. The outer regions might have fewer stars, while the inner regions might have more. This could affect the rate of close stellar encounters. In denser regions, stars pass by each other more frequently. These encounters can disturb planetary orbits, potentially destabilizing systems that were previously stable. On the other hand, in less dense regions, stellar encounters would be even rarer than they are today. The overall effect is hard to predict. Some planetary systems might be disrupted by the merger, while others might be unaffected. The galaxy as a whole would remain habitable for life, but the distribution of habitable environments might change. Another exotic possibility to consider is the formation of hypervelocity stars. During the merger, gravitational interactions can accelerate stars to extremely high velocities. Some stars could achieve velocities high enough to escape the galaxy entirely, becoming hypervelocity stars that shoot off into intergalactic space. We already know that hypervelocity stars exist. Astronomers have identified several dozen of them leaving the Milky Way at speeds of up to 1 million miles per hour. Most of these are thought to have been accelerated by close encounters with the supermassive black hole at the galactic center. During the galaxy merger, the number of hypervelocity stars could increase dramatically. The gravitational chaos would create many opportunities for stars to be accelerated to escape velocity. Some models suggest that millions of stars could be ejected during a major merger. These hypervelocity stars would carry any planetary systems with them. Imagine an entire solar system being flung out of the galaxy, destined to drift through intergalactic space forever. Any life on planets in such a system would suddenly find itself in a very different cosmic environment, surrounded by the vast emptiness between galaxies. The intergalactic medium is not truly empty. There is a thin plasma of ionized hydrogen and helium between galaxies, heated to millions of degrees by shocks and radiation. A planet traveling through this medium would be exposed to this hot plasma, though the effects would probably be minimal, given how thin the plasma is. More significantly, the intergalactic travelers would lose access to the resources of a galaxy. No nearby stars to colonize, no interstellar gas to harvest, no cosmic neighbors to communicate with, just endless darkness stretching in all directions, with the glow of receding galaxies growing fainter as the universe expands. For any intelligent beings in such a situation, it would be a profound kind of isolation. They would have all the resources of their own solar system, but nothing beyond. If they had achieved space travel within their system, they could continue to thrive. But reaching another star would become essentially impossible, with the nearest stars millions or billions of light years away. This kind of scenario is probably rare, but it illustrates the range of outcomes possible during a galaxy merger. Some stellar systems will remain in the merged galaxy, with relatively little change to their circumstances. Others might find themselves in very different situations, flung into the void or moved to new galactic neighborhoods. Let us also consider what the collision might teach us about the nature of gravity and dark matter. Major galaxy mergers are natural laboratories for testing our theories of physics. The gravitational interactions are so strong and so complex that they provide stringent tests of our understanding. One key question is whether dark matter behaves as our theories predict during galaxy collisions. The standard model of dark matter assumes that dark matter particles interact with each other only through gravity, not through any other force. This means dark matter halos should pass through each other during collisions, with the particles barely noticing each other. Observations of colliding galaxy clusters have provided some of the best evidence for this behavior. In systems like the Bullet Cluster, astronomers can map the distribution of dark matter using gravitational lensing, where the dark matter bends the light from more distant objects. These maps show that the dark matter halos have passed through each other and are now on opposite sides of the collision, while the hot gas between the clusters has collided and been left behind. The Milky Way Andromeda merger will provide another opportunity to study dark matter behavior, though we will not be around to see it directly. Instead, astronomers will continue to study other merging systems and refine our understanding of how dark matter behaves. Another area of interest is the formation of gravitational waves during galaxy mergers. As we discussed, the merger of supermassive black holes will produce a powerful burst of gravitational waves. This burst will propagate outward at the speed of light, carrying information about the merger across the universe. Future gravitational wave observatories might be able to detect such bursts from merging galaxies throughout the cosmos. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave detector that should be sensitive to the low-frequency waves produced by supermassive black hole mergers. When LISA launches, it will open a new window on the universe, allowing us to study black hole mergers in ways that are currently impossible. The gravitational waves from a supermassive black hole merger carry detailed information about the masses and spins of the black holes, the dynamics of the merger, and the properties of space-time itself. By studying these waves, astronomers hope to test general relativity in the strong field regime, where the effects of gravity are most extreme. The Milky Way Andromeda black hole merger will be one such event, though of course the gravitational waves will not reach potential detectors until billions of years after the merger. But other black hole mergers are happening all the time throughout the universe. Every major galaxy merger eventually results in a black hole merger. By studying these events in distant galaxies, we can learn about the physics that will one day play out in our own cosmic backyard. Let us now return to the human perspective and think about what all of this means for our understanding of our place in the cosmos. The collision between Andromeda and the Milky Way is just one event in a vast and ancient universe. But it is our event, the great transformation that will reshape our galactic home. Throughout human history, people have looked up at the night sky and wondered about their place in the universe. The stars seem fixed and eternal, unchanging patterns that generations could rely on. Even as human civilizations rose and fell, the constellations remained. Now we know that this apparent constancy is an illusion. The stars are moving, the galaxy is changing, and in the cosmic future, everything we see in the night sky will be transformed. The Milky Way will merge with Andromeda. The familiar constellations will be disrupted. A new galaxy will be born. This knowledge can be unsettling. There is something comforting about believing that the heavens are permanent and unchanging. But there is also something profound about understanding the true nature of cosmic change. We are privileged to live in an age when science has revealed these deep truths about the universe. The ancient Greek philosophers thought the heavens were perfect and eternal, fundamentally different from the changing world below. They could not have imagined that the stars are themselves suns, that the Milky Way is a galaxy among billions, or that our galaxy is destined to collide with another. These insights are the hard-won achievements of centuries of scientific inquiry. Every generation of astronomers has contributed to our understanding. Galileo turned his telescope to the sky and saw the moons of Jupiter and the phases of Venus. Herschel mapped the structure of the Milky Way and discovered that we live in a disc-shaped system. Hubble showed that the universe extends far beyond our galaxy, with billions of other galaxies scattered through space. And modern astronomers have measured the motions of these galaxies and predicted their future collisions. We are the beneficiaries of this cumulative knowledge. We can understand the universe in ways that our ancestors could not have imagined, and we can pass this knowledge on to future generations, building the foundation for even deeper understanding to come. The collision between Andromeda and the Milky Way reminds us that we are part of a story much larger than ourselves. Our individual lives are brief, but we are connected to a cosmos that spans billions of years. The atoms in our bodies were forged in ancient stars. The ground we walk on was formed from cosmic dust, and one day, billions of years from now, the matter that makes us up will be part of a new galaxy, shaped by the collision we have been discussing. There is a kind of immortality in this perspective. Not personal immortality, but a connection to something that transcends individual existence. We are made of the universe, and to the universe we will return. The changes that will reshape the galaxy are the same kinds of changes that have always been happening, part of the ongoing evolution of the cosmos. This perspective can also inspire humility. We often get caught up in the concerns of daily life, thinking that our problems and achievements are of cosmic importance. But the universe is vast, and our place in it is small. The collision between Andromeda and the Milky Way will happen regardless of anything humans do or do not do. We are witnesses to cosmic processes, not controllers of them. At the same time, there is something remarkable about the fact that we can understand these processes at all. The universe has produced beings capable of comprehending its own workings. Through science, we have extended our senses far beyond their natural limits. We can see galaxies billions of light years away. We can understand events that will happen billions of years in the future. We can grasp the laws that govern the behavior of matter and energy throughout the cosmos. This is an extraordinary achievement. In all the vast universe, so far as we know, only on this one small planet has matter organized itself to contemplate the structure of reality. We may be small, and our lives may be brief, but we can think big thoughts and understand deep truths. The collision between Andromeda and the Milky Way is one of those deep truths. It connects our present moment to the far future, linking the world we know to a transformation we can only imagine. It reminds us that change is the fundamental nature of the universe, that nothing is permanent, and that even the grandest structures are subject to evolution and transformation. Let us spend some time now discussing the tools and techniques that astronomers use to study galaxies and predict their futures. Understanding how we know what we know adds depth to our appreciation of these cosmic phenomena. The most basic tool of astronomy is light. By collecting and analyzing light from distant objects, astronomers can learn an enormous amount about the universe. The light tells us about the composition of stars and galaxies, their temperatures, their motions, and their distances. One crucial technique is spectroscopy, the analysis of light broken down into its component wavelengths. When light passes through a prism or a diffraction grating, it spreads out into a spectrum with different colors corresponding to different wavelengths. This spectrum contains information about the source of the light. Every element produces a unique pattern of lines in a spectrum, a kind of fingerprint that identifies it. By looking at the spectral lines from a star or galaxy, astronomers can determine what elements are present. They can also measure how the spectral lines are shifted from their normal positions, which tells them about the motion of the source. This is how we know that Andromeda is approaching us. The spectral lines from Andromeda are blue shifted, meaning they are shifted toward shorter wavelengths. This indicates that Andromeda is moving toward us, compressing the light waves just as a moving ambulance compresses its siren sound. The amount of blue shift tells us the velocity of the approach. Another essential tool is the measurement of distances. Knowing how far away something is allows us to understand its true size, brightness, and motion. Astronomers have developed many techniques for measuring cosmic distances, forming what they call the cosmic distance ladder. For relatively nearby objects, astronomers can use parallax, the apparent shift in position of an object when viewed from different locations. As the Earth orbits the Sun, nearby stars appear to move slightly against the background of more distant stars. By measuring this shift, astronomers can calculate the distance to the star. For more distant objects, other techniques are needed. One powerful method uses Cepheid variable stars, stars whose brightness pulsates in a regular pattern. The period of the pulsation is related to the star's true brightness, so by measuring the period and the apparent brightness, astronomers can calculate the distance. This technique was used by Edwin Hubble in the 1920s to measure the distance to Andromeda. He identified Cepheid variables in Andromeda and showed that they were far too distant to be part of the Milky Way. This proved that Andromeda was a separate galaxy, revolutionizing our understanding of the universe. Modern astronomers use additional techniques to measure distances even more precisely. Type Ia supernovae, for example, have a characteristic brightness that makes them useful as standard candles. By observing these supernovae in distant galaxies, astronomers can measure distances to the farthest reaches of the observable universe. The Gaia Space Telescope, launched by the European Space Agency in 2013, has provided the most detailed map of the Milky Way ever created. Gaia has measured the positions, distances, and motions of over 1 billion stars with unprecedented precision. This data has revolutionized our understanding of the Milky Way structure and dynamics. Gaia has also improved our predictions for the Andromeda collision. By precisely mapping the motions of stars in the Milky Way, astronomers can better understand the mass distribution in our galaxy, including the dark matter halo. This information feeds into the simulations that predict how the collision will unfold. Computer simulations are another essential tool for understanding galaxy dynamics. The gravitational interactions in a galaxy are far too complex to solve analytically. Instead, astronomers use powerful computers to simulate the behavior of billions of particles, each representing a clump of stars or dark matter. These simulations start with the current conditions of the galaxies and then calculate how they evolve over time. The computers solve the equations of gravity for every particle, tracking how they move and interact. By running the simulation forward, astronomers can see what will happen in the future. The accuracy of these simulations depends on how well we know the current conditions and how many particles can be included. Modern simulations can include billions of particles and run for millions of time steps. The results are remarkably realistic, matching observations of real galaxy collisions with impressive fidelity. For the Milky Way Andromeda collision specifically, astronomers have run many simulations with different initial conditions. They vary the masses of the galaxies, the extent of the dark matter halos, and the sideways motion of Andromeda. By exploring this range of possibilities, They can determine which aspects of the collision are robust predictions and which depend on uncertain parameters. The main conclusions are robust. The galaxies will collide, they will merge. The result will be an elliptical galaxy. The black holes will eventually merge. These outcomes are consistent across all reasonable assumptions about the initial conditions. Some details are more uncertain. The exact timing of the first encounter could vary by several 100 million years, depending on the precise velocity of Andromeda. The number of passes before final merger could be affected by the details of the dark matter distribution. The fate of any particular star, including our Sun, depends on initial conditions that we cannot measure precisely. But the big picture is clear. Cosmic transformation is coming. The Milky Way, as we know it, will not last forever. Change is the nature of the universe, and our home galaxy is no exception. Let us now consider some of the philosophical implications of the galaxy collision. How should we think about an event so far in the future? Does it matter to us today that the galaxy will be transformed in billions of years? One perspective is that the distant future is irrelevant to our present concerns. We will not be around to see the collision. Our civilization, if it still exists, will have changed beyond recognition long before Andromeda arrives. Why should we care about events so far removed from our lives? There is some validity to this view. We cannot affect the collision or be affected by it directly. Our practical priorities should focus on the near-term challenges facing our civilization. Climate change, nuclear, weapons, pandemic diseases, and other near-term risks deserve more attention than a galaxy collision billions of years away. But there is also value in contemplating the long-term future of the cosmos. It provides perspective on our place in the universe. It connects us to something larger than our immediate concerns. It reminds us that the universe is vast and ancient and will continue long after we are gone. This kind of cosmic perspective can be psychologically valuable. When we are overwhelmed by the problems of daily life, it can help to remember that we are part of a grand cosmic story. Our problems are real, but they are not the whole of existence. The universe goes on, and in some small way, we are part of it. The galaxy collision also raises interesting questions about the long-term future of intelligence in the universe. Will any form of consciousness be around to witness the merger? Will intelligent beings in the far future know about our civilization? Or will all trace of us be lost? These are questions we cannot answer. The timescales involved are too long, and the evolution of intelligence is too unpredictable. But they are fascinating to contemplate. They connect our present moment to a vast sweep of cosmic time, reminding us that we are part of an ongoing story. Some philosophers have argued that the long-term future of the universe should be a moral concern. If intelligent life could persist for billions or trillions of years, then the potential for future flourishing is immense. We have a responsibility, they argue, to ensure that this potential is realized. From this perspective, the galaxy collision is relevant to our present choices in an indirect way. Actions we take today could affect the long-term trajectory of civilization. If we develop the technologies and institutions needed for long-term survival, our descendants might still be around to witness the cosmic transformations ahead. This is speculative, of course. We cannot predict what will happen to human civilization over even the next few centuries, let alone billions of years. But the possibility of a very long future gives weight to our present choices. We are not just living for ourselves, but potentially for countless future generations. The galaxy collision also raises questions about the nature of identity and continuity. The Milky Way has a certain identity, a shape and structure that distinguishes it from other galaxies. When it merges with Andromeda, that identity will be lost. Something new will emerge, but the Milky Way as we know it will be gone. Is this a kind of death for the galaxy? Or is it a transformation, a continuation in a different form? These questions are hard to answer because galaxies are not the kind of entities that have clear boundaries and essences. They are collections of stars, gas, and dark matter, constantly changing and evolving. In one sense, the Milky Way is already different from what it was billions of years ago. It has grown through mergers. Its stars have been born and died. Its structure has evolved. The galaxy we see today is not the same as the galaxy that existed when the Earth formed. Change is constant, even if it is usually slow. From this perspective, the Andromeda collision is just a more dramatic example of the ongoing change that characterizes all galaxies. The Milky Way has always been changing. The collision will accelerate that change, transforming the galaxy into something new. But transformation is not the same as annihilation. The stars will continue to shine. New stars will form. The matter that makes up the galaxy will persist, just in a different arrangement. This might provide some comfort if we are inclined to mourn the eventual loss of the Milky Way. Our galactic home will be transformed but not destroyed. Something new will take its place, carrying forward the matter and energy of the old. In the grand scheme of things, this is how the universe has always worked. Let us now look at some of the specific scientific discoveries that have shaped our understanding of the Andromeda collision. The story of how we learned about this cosmic event is a fascinating tale of scientific progress. The first step was recognizing that Andromeda is a galaxy at all. For centuries, it was known only as a fuzzy patch of light in the night sky. The Persian astronomer Abd al-Rahman al-Sufi described it in the 10th century as a little cloud. Later, astronomers called it a nebula, assuming it was a cloud of gas within our own Milky Way. The true nature of Andromeda was revealed in the 1920s through the work of Edwin Hubble. Using the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble identified Cepheid variable stars in Andromeda. By measuring their pulsation periods and apparent brightnesses, he calculated that Andromeda was about 900,000 light-years away. This distance was far beyond the size of the Milky Way as he then understood. Andromeda had to be a separate galaxy, not a cloud within our own. This discovery was revolutionary, expanding the known universe by a factor of millions. Suddenly, the Milky Way was not the whole cosmos, but just one galaxy among countless others. Hubble's distance estimate turned out to be too small. We now know that Andromeda is about 2.5 million light-years away, not 900,000. But the key insight was correct. Andromeda is another galaxy, similar in size and structure to our own. The next step was measuring the motion of Andromeda toward us. This came from spectroscopic observations that detected the blue shift of Andromeda's light. The first such measurement was made by Vesto Slipher at Lowell Observatory in 1912, even before Hubble proved that Andromeda was a separate galaxy. Slipher measured that the light from Andromeda was shifted toward shorter wavelengths, indicating motion toward us. His measurement gave a velocity of about 300 kilometers per second toward the Sun. This was an extraordinarily high velocity, faster than any object within the Milky Way. At the time, Slipher interpreted this as motion of a nebula within our galaxy. Only later, after Hubble's discovery, did the significance become clear. Andromeda was not just a cloud moving within the Milky Way. It was an entire galaxy approaching from millions of light-years away. Modern measurements have refined the velocity estimate. The current best value for Andromeda's radial velocity, its velocity directly toward us, is about 110 kilometers per second. However, this is measured relative to the Sun, which is itself moving around the Milky Way center. When corrected for the Sun's motion, the velocity of Andromeda toward the Milky Way's center is higher, about 400 kilometers per second. Measuring the radial velocity was relatively straightforward, since it just required analyzing the spectrum of Andromeda's light. Much harder was measuring the tangential velocity, the sideways motion across the sky. This motion is tiny because Andromeda is so far away. Even moving at hundreds of kilometers per second, it would take thousands of years for Andromeda to shift its position by an amount detectable by eye. For decades, astronomers could only estimate the tangential velocity indirectly, using theoretical arguments. They knew it had to be small enough for the collision to occur, but they could not measure it directly. This limited the precision of predictions about the collision. The breakthrough came in 2012, when astronomers used the Hubble Space Telescope to measure the tangential velocity directly. By comparing images taken several years apart, they detected the tiny shift in Andromeda's position relative to background galaxies. The measurement required exquisite precision, detecting motions of millionths of an arcsecond. The result was that Andromeda's tangential velocity is indeed small, about 17 kilometers per second. This confirmed that Andromeda is heading almost directly toward us, with only a slight sideways motion. The collision is essentially head-on. With both the radial and tangential velocities measured, astronomers could predict the collision with much greater confidence. They could also determine that the Triangulum Galaxy, the third largest galaxy in the local group, is probably gravitationally bound to Andromeda and will participate in the merger. More recent observations from the Gaia satellite have further refined these measurements. Gaia has mapped the motions of stars within both the Milky Way and some nearby dwarf galaxies, providing better constraints on the mass distribution and hence the gravitational interactions. The current best prediction is that the first close encounter will occur in about 4.5 billion years. There is an uncertainty of perhaps 500 million years in this estimate, depending on exactly how the mass is distributed in the dark matter halos. But the general picture is clear and robust. Let us now discuss some of the technologies that future astronomers might use to study the collision as it unfolds. We will not be around to see it, but our distant descendants, if they exist, will have front row seats to one of the great cosmic events of the local universe. By the time of the collision, billions of years of technological development will have occurred. It is impossible to predict what technologies might exist at that point, but we can speculate about what capabilities would be useful for studying the merger. Advanced telescopes would be essential for observing the collision in detail. Future telescopes might be based in space, far from any planetary atmosphere, with apertures spanning kilometers rather than meters. They might use active optics that can adjust in real time to maximize resolution. They might observe across the entire electromagnetic spectrum, from radio waves to gamma rays. Such telescopes could track the motions of individual stars as the galaxies interact. They could map the structure of the tidal tails and bridges forming between the galaxies. They could observe the starbursts in the compressed gas clouds, watching new stars ignite in real time. Gravitational wave detectors would be particularly valuable for observing the black hole merger. Advanced versions of LISA could detect the gravitational waves from the approaching black holes, tracking their spiral dance over millions of years. The final merger would produce a signal loud enough to be detected throughout the local universe. Artificial intelligence and advanced computing would be needed to process the enormous amounts of data generated by these observations. The collision involves billions of stars and countless gas clouds, all interacting gravitationally. Tracking and understanding this complexity would require computational resources far beyond anything we have today. Perhaps the most dramatic possibility is that future beings might travel to other locations within the merging galaxies to observe the collision from different perspectives. A civilization that has spread across the stars might have observers in many locations, coordinating their observations to build a complete picture of the merger. Such observers might be stationed in the tidal tails, watching the cause from outside. They might ride along with stars being flung into intergalactic space. They might approach the central black holes, observing the intense activity as gas falls inward. Each perspective would provide different insights into the physics of the merger. Of course, all of this is highly speculative. We have no idea whether any intelligent beings will exist when the collision happens. We do not know if our descendants will have spread to other stars, or if they will have gone extinct. The future is radically uncertain on such long timescales, but it is fascinating to imagine. The collision between Andromeda and the Milky Way will be one of the great events of the local universe, a transformation that will reshape our cosmic home. If anyone is around to see it, they will witness something truly spectacular. As we conclude our exploration of this cosmic event, let us reflect on what we have learned and what it means. The collision between the Milky Way and Andromeda is a certainty. The physics is clear. The observations are precise. The simulations are consistent. Our galaxy will be transformed. This transformation will take place over timescales that dwarf human history. The first close encounter is 4.5 billion years away. The final merger will not be complete for another 2 billion years after that. These are numbers so large that they are difficult to comprehend in human terms. But we can comprehend them, at least intellectually. We can understand that the universe operates on these vast scales. We can appreciate that our present moment is just one instant in a cosmic history spanning billions of years. We can connect our existence to the grand sweep of cosmic evolution. The Milky Way is our home. It has been home to our ancestors for as long as life has existed on Earth. The band of light across the night sky has inspired wonder and curiosity in countless generations. It is natural to feel some sense of loss at the thought that our galactic home will eventually be transformed beyond recognition. But transformation is the nature of the universe. Stars are born and die. Galaxies form and merge. The cosmos is constantly changing, evolving, becoming something new. The collision between Andromeda and the Milky Way is just one example of this cosmic creativity. And from transformation comes new possibilities. The merger will trigger the formation of new stars. New planets will form around those stars. New opportunities for life and intelligence will emerge. The galaxy that rises from the merger, Milky, will be a new cosmic home, different from the Milky Way, but no less capable of supporting the wonders of the universe. If you have watched this far, you have joined me on a journey through billions of years of cosmic history. You have learned about gravity and dark matter, about tidal tails and starbursts, about supermassive black holes and gravitational waves. You have contemplated the far future and reflected on what it means for our place in the universe. I hope this journey has been as fascinating for you as it has been for me to guide you through it. The universe is full of wonders, and the collision between Andromeda and the Milky Way is one of the greatest wonders of all. It connects our present moment to the deep future, reminding us that we are part of something vast and ancient and ongoing. Thank you for watching. If you enjoyed this exploration of cosmic collision, please consider subscribing to the channel and sharing this video with others who might be interested. Every view and share helps us bring more content like this to curious minds around the world. The night sky above us is full of stories. The stars have tales to tell about the history of the universe and the future that awaits. Keep looking up, keep wondering, keep exploring. The cosmos is waiting to be understood. Until next time, may your skies be clear and your curiosity boundless. Let us delve even further into some of the remarkable aspects of this cosmic story that we have not yet fully explored. There are so many fascinating details about galactic collisions that deserve our attention and wonder. Consider the fate of planetary nebulae during the merger. Planetary nebulae are the glowing shells of gas expelled by dying sun-like stars at the end of their lives. These beautiful objects dot our galaxy, showing the final chapter of stellar evolution for smaller stars. During the galaxy merger, these nebulae will continue to form as stars die. The interesting thing is that the rate of planetary nebula formation might actually increase during certain phases of the merger. The enhanced star formation triggered by the collision will produce many new stars. Some of these will be similar in mass to our Sun, and they will eventually go through the red giant phase and produce planetary nebulae. Billions of years after the initial starburst, a second wave of these colorful objects will appear throughout Milky. Each planetary nebula will be a monument to a star that once shone. The central white dwarf, the hot, dense core of the dead star, will slowly cool over billions of years. The nebula itself will expand and fade, its glowing gases dispersing into the interstellar medium. This cycle of stellar death and rebirth will continue throughout the history of Milky, just as it does in the Milky Way and Andromeda today. Let us also think more about the interstellar medium, the gas and dust that fills the space between stars. This material is the raw stuff from which new stars form. It is enriched with heavy elements produced in the cores of previous stellar generations. Carbon, oxygen, iron, and all the other elements necessary for life are spread through the interstellar medium, waiting to be incorporated into new stars and planets. During the galaxy merger, the interstellar medium will be dramatically affected. The compression of gas clouds will trigger intense star formation, as we have discussed. But the gas will also be heated and stirred by the gravitational chaos. Shockwaves from supernova explosions will ripple through the medium. Jets from the active galactic nucleus could clear out channels of low-density material. The end result will be a different distribution of interstellar gas than what we see in spiral galaxies today. Elliptical galaxies typically have less interstellar gas than spirals. Much of the gas in the Milky Way and Andromeda will be used up in the starburst or expelled by supernovae and stellar winds. What remains will be distributed more uniformly, without the dense spiral arm structures that characterize disk galaxies. This has implications for future star formation in Milky. Without dense gas clouds, the rate of new star formation will decline. Eventually, the galaxy will run out of gas for making new stars. The existing stars will age and die, and the galaxy will gradually fade. This is the ultimate fate of all elliptical galaxies, a slow dimming over trillions of years. But this dimming will take a very long time. Even after the merger is complete, Milky will have enough gas to form new stars for billions of years. The decline will be gradual, with the galaxy remaining bright and active for longer than the current age of the universe. Our descendants, if they exist, will have plenty of time to adapt to the changing galactic environment. Let us now explore the concept of galactic archaeology, the study of a galaxy's past through the stars and structures that remain today. Astronomers use galactic archaeology to understand the history of the Milky Way, tracing past merger events and star formation episodes through the chemical signatures and orbital properties of stars. In Milkomeda, galactic archaeology will be even more complex and fascinating. The stars from the original Milky Way and Andromeda will be mixed together, but their chemical and kinematic signatures will still preserve information about their origins. Future astronomers will be able to identify which stars came from which progenitor galaxy. The challenge will be immense. After billions of years of mixing, the stars will be scattered throughout the merged galaxy. Their original orbits will be long forgotten, replaced by new orbits around the combined center of mass. But the chemical abundances in their atmospheres will remain unchanged, preserving a record of where and when they formed. Stars that formed in the Milky Way will have slightly different ratios of heavy elements compared to stars from Andromeda. These differences arise because the two galaxies have had different star formation histories. By analyzing the chemistry of individual stars in Milkomeda, astronomers could reconstruct which came from which original galaxy. This kind of analysis is already being done today. The Gaia satellite and ground-based spectroscopic surveys are mapping the chemical abundances of millions of stars in the Milky Way. Astronomers have identified streams of stars that came from dwarf galaxies absorbed by our galaxy in the past. Similar techniques will be applicable to understanding the merger history of Milkomeda. The stellar archaeology of Milkomeda will tell a story of cosmic collision and transformation. It will reveal how two great spiral galaxies came together to form something new, and it will connect the far future of the galaxy back to its origins, including the present day when the collision was still billions of years away. Speaking of the present day, let us consider what we can observe right now that gives us insight into our galactic future. The Andromeda Galaxy is visible to the naked eye under dark skies, appearing as a faint smudge in the constellation Andromeda. With binoculars or a small telescope, you can see its elongated shape and bright central core. What you are seeing when you look at Andromeda is light that left that galaxy about 2.5 million years ago. This light has been traveling through the void of space all that time, carrying information about Andromeda across the cosmic distance. In those 2.5 million years, Andromeda has moved closer to us by a significant amount, but the change is tiny compared to the remaining distance. Astronomers have calculated what Andromeda will look like from Earth at various points in the future. In about 2 billion years, it will appear noticeably larger than it does today. In 4 billion years, it will dominate the night sky, stretching across dozens of degrees. And during the collision itself, the combined light of both galaxies will transform the heavens into something unrecognizable. Let us also consider the role of magnetic fields in the galaxy merger. Both the Milky Way and Andromeda have magnetic fields that permeate their interstellar media. These fields are weak compared to a refrigerator magnet, but they extend across thousands of light years and play important roles in galactic dynamics. Magnetic fields affect how gas moves within galaxies. They provide pressure support against gravity. They channel charged particles along field lines. They influence the formation of stars and the propagation of cosmic rays. During the galaxy merger, these magnetic fields will be stretched, compressed, and tangled in complex ways. The interaction of the magnetic fields from both galaxies will generate turbulence in the interstellar medium. This turbulence can accelerate particles to high energies, producing cosmic rays that travel throughout the galaxy. The cosmic ray flux in the merged galaxy might be enhanced for a time, until the turbulence dies down and the magnetic fields settle into a new configuration. Astronomers study galactic magnetic fields using radio observations. When charged particles spiral around magnetic field lines, they emit radio waves with a characteristic polarization. By mapping this polarized radio emission, astronomers can trace the structure of the magnetic field. Similar observations of Milky would reveal how the magnetic fields evolved during and after the merger. Another aspect worth considering is the globular cluster population of the merged galaxy. Globular clusters are ancient collections of hundreds of thousands of stars, bound together by gravity. The Milky Way has about 150 known globular clusters. Andromeda has even more, perhaps around 500. When the galaxies merge, their globular cluster populations will combine. Milky will inherit all the globular clusters from both parent galaxies, plus any new clusters that might form during the starburst phase of the merger. The total population could exceed 600 globular clusters, making Milky one of the richer globular cluster systems in the local universe. These globular clusters will provide a fossil record of the merger. Astronomers will be able to distinguish clusters that formed in the Milky Way from those that formed in Andromeda based on their chemical compositions and positions within the merged galaxy. Some clusters might be identifiable as having formed during the merger itself, created from the compressed gas during the collision. Globular clusters are among the oldest objects in any galaxy. Some of the clusters in the Milky Way and Andromeda formed over 12 billion years ago when the universe was young. These ancient objects will survive the merger and continue to orbit around Milky, carrying the memory of the earliest epochs of cosmic history. Let us now think about what the merger means for the local group as a whole. The local group is the collection of galaxies that are gravitationally bound to the Milky Way and Andromeda. It includes the Triangulum Galaxy, the Large and Small Magellanic Clouds, and several dozen dwarf galaxies. After the Milky Way-Andromeda merger, the local group will be dominated by the single massive elliptical galaxy Milky. The smaller members of the group will orbit around this central giant. Some may eventually be absorbed by Milky through additional minor mergers. Others may be flung out of the group by gravitational interactions. The Triangulum Galaxy is particularly interesting in this context. It is the third largest galaxy in the local group, with about 40 billion stars. Simulations suggest that Triangulum might merge with Milky, or it might be ejected from the group entirely. The outcome depends on the exact orbital parameters, which are not yet known with sufficient precision. The Magellanic Clouds are another interesting case. These two irregular dwarf galaxies are currently satellites of the Milky Way, orbiting at distances of about 160,000 and 200,000 light-years respectively. During the merger, their orbits will be disrupted by the changing gravitational field. The other dwarf galaxies in the local group face similar uncertain futures. Each one will be affected by the changing gravitational landscape as the two major galaxies come together. Some will be absorbed, some will survive as satellites of Milky, and some might become intergalactic wanderers, ejected by the violence of the merger. As we approach the true conclusion of our cosmic journey, let us take a moment to appreciate the remarkable nature of the scientific knowledge that makes this understanding possible. Just a century ago, we did not even know that galaxies existed beyond our own Milky Way. The idea that our galaxy would one day merge with another was not just unknown, it was unimaginable. Today, we can predict this merger with confidence. We know when it will happen, how it will unfold, and what the result will be. This knowledge comes from centuries of scientific progress, from the careful accumulation of observations and theories that have revealed the true nature of the cosmos. Astronomy is one of the oldest sciences, practiced in some form by every human civilization throughout history. But the astronomy of today is radically different from the astronomy of our ancestors. We have tools they could not have dreamed of. Telescopes that can see billions of light years into space. Satellites that can measure the positions of stars with unprecedented precision. Computers that can simulate the behavior of billions of particles over billions of years. These tools have given us a view of the universe that is both humbling and inspiring. We know our place in the cosmic order. We are tiny beings on a small planet orbiting an ordinary star in one arm of a typical spiral galaxy. We are not at the center of anything. The universe does not revolve around us. And yet, we have the ability to understand the universe in profound ways. We can grasp the forces that shape galaxies. We can predict the future of our cosmic home. We can connect our existence to the vast sweep of cosmic history, from the Big Bang to the far future when the stars themselves have faded. This is the gift of science. It reveals the truth about the cosmos, even when that truth challenges our assumptions or shows us our insignificance. But in revealing our smallness, science also reveals our uniqueness. We are the universe contemplating itself. Through us, the cosmos has developed the ability to understand its own nature. The collision between Andromeda and the Milky Way is one chapter in this cosmic story. It is a story of change and transformation, of old structures giving way to new ones. It is a story that connects our present moment to a future billions of years away, and it is a story that we, despite our brief lives and limited perspectives, can understand and appreciate. So as we conclude, remember what you have learned. Andromeda is coming. The collision will transform our galaxy. A new cosmic home will emerge from the merger. And through it all, the universe will continue its eternal dance of creation and destruction, order and chaos, beginning and ending. Thank you for joining me on this journey through cosmic time. If you found this exploration valuable, please share it with others who might appreciate it. Subscribe to the channel for more journeys into the wonders of the universe. And remember to look up at the night sky whenever you can, for the stars above us tell stories of unimaginable scope and beauty. The cosmos is vast and ancient, but we are here now, able to understand at least a small part of it. That is a precious gift, and one we should cherish. Keep exploring, keep wondering, keep looking up at the stars. This has been Cosmic Drift. Until next time, may your curiosity never fade, and may the universe continue to reveal its secrets to you. But before we truly part ways, let us explore a few more wonders that await in this grand cosmic event. There are aspects of the collision we have only touched upon that deserve deeper consideration. Think about the neutron stars scattered throughout both galaxies. These are the ultra-dense remnants of massive stars that exploded as supernovae. A single teaspoon of neutron star material would weigh as much as a mountain on Earth. There are estimated to be around 1 billion neutron stars in the Milky Way alone, and a similar number in Andromeda. When the galaxies merge, these neutron stars will continue their existence largely unaffected by the collision. They are so small and so dense that the gravitational chaos of the merger will not disrupt them. They will simply find themselves in new orbits around the combined galactic center, pulsing steadily as they have for millions or billions of years. Some neutron stars are pulsars, rapidly rotating objects that emit beams of radio waves like cosmic lighthouses. As they spin, these beams sweep across space, and if Earth happens to be in the path of the beam, we detect regular pulses of radio emission. Pulsars are some of the most precise clocks in the universe, keeping time with incredible accuracy. During and after the merger, pulsars in Milky will continue to tick away, their precise pulses marking the passage of time in the new galaxy. Future astronomers could use these pulsars for navigation, timing, and fundamental physics experiments, just as we do today. The pulsars will be one of the few things that remain unchanged through the cosmic transformation. Let us also consider the brown dwarfs. These are objects too small to sustain hydrogen fusion in their cores, making them failed stars. They glow dimly with the heat left over from their formation, slowly cooling over billions of years. There may be more brown dwarfs in the Milky Way than actual stars, though their faintness makes them hard to count. Brown dwarfs will survive the merger just as stars do, being too small and too cool to attract much attention. They will simply drift through the collision, eventually settling into orbits around the center of Milky. These dim objects will make up a significant portion of the merged galaxy's mass, contributing to its gravitational structure even though they produce almost no light. Some brown dwarfs have planets orbiting around them. These would be cold, dark worlds, warmed only by the feeble glow of their failed star hosts. If any such planets harbor life, those life forms would experience the galaxy merger as a gradual change in their night sky, assuming they could see anything at all in the dim environment around a brown dwarf. Now let us think about what astronomers call the circumgalactic medium. This is the diffuse gas that surrounds galaxies, extending far beyond the visible disk. The Milky Way is thought to have a massive halo of hot gas, with a mass perhaps comparable to all the stars in the galaxy combined. When the two galaxies merge, their circumgalactic media will interact. The hot gas halos will collide and mix, creating shockwaves and turbulence. Some of this gas may be heated to even higher temperatures, while other portions may cool and fall toward the center of the merged galaxy. This circumgalactic gas is important for the future of Milky. It represents a reservoir of material that could potentially fuel future star formation. As the gas cools and sinks toward the galactic center, it could provide fresh fuel for making new stars, extending the period of star formation in the merged galaxy. The interaction of the circumgalactic medium is difficult to observe directly because the gas is so diffuse and hot. But X-ray telescopes can detect the emission from this hot gas, and astronomers are beginning to map the halos around nearby galaxies. Understanding these halos will improve our predictions for what happens when they collide. Consider also the cosmic rays that fill both galaxies. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light. They are accelerated by supernova explosions, pulsar winds, and other energetic events. The cosmic ray flux in the Milky Way is continuously replenished by new sources. During the merger, the cosmic ray population will be affected in several ways. New supernovae from the starburst will inject fresh cosmic rays. The turbulent magnetic fields will accelerate particles to high energies. The overall cosmic ray flux might increase significantly during the most active phases of the merger. High cosmic ray fluxes can have biological effects on any life that exists in the galaxy. On Earth, we are protected by our planet's magnetic field and atmosphere, which shield us from most cosmic rays. But unprotected life in space, or on planets with weaker magnetic fields, could be affected by increased radiation during the merger. This is another reason why the collision, while not directly harmful to most planetary systems, could have subtle effects on habitability throughout the galaxies. The changing cosmic ray environment would add another variable to the complex equation of where and how life can exist. Let us also think about the dust grains scattered throughout both galaxies. These tiny particles, made of silicates, carbon, and ice, are responsible for much of the obscuration in astronomical images. Dust absorbs and scatters light, making some regions of galaxies appear dark. During the merger, dust will be swept up in the gas flows and compressed in shock waves. Some dust will be destroyed by the intense radiation in starburst regions. New dust will form in the ejecta of dying stars. The distribution and properties of dust in Milky will be different from what we see in the Milky Way today. Dust plays a crucial role in star formation. It helps gas clouds cool, allowing them to collapse under their own gravity. The surfaces of dust grains provide sites where molecules can form, including the complex organic molecules that might be precursors to life. By affecting the dust distribution, the merger will indirectly influence where and how efficiently new stars can form. Now let us reflect on the cultural and philosophical impact that knowledge of the collision has had on humanity. Learning that our galaxy is destined to merge with another has given us a new perspective on our place in the universe. Before we understood galactic dynamics, people could imagine the night sky as eternal and unchanging. The stars seem fixed in their patterns, rotating around the celestial pole in predictable cycles. Only the planets wandered among the stars, and even they followed regular paths. Now we know that the heavens are far more dynamic than our ancestors imagined. Galaxies move, they collide, they merge. The very fabric of cosmic structure is in constant flux, evolving over timescales we can barely comprehend. This knowledge can inspire both awe and humility. We are tiny creatures on a small planet, witnesses to cosmic processes we cannot control. But we are also the beings who discovered these truths, who pieced together the story of cosmic evolution from observations and mathematics. In understanding our insignificance, we have also demonstrated our remarkable capacity for knowledge. Some people find comfort in the long timescales involved. The collision is billions of years away, far beyond any human concern. Our civilization will have risen and fallen many times before Andromeda arrives. Whatever our descendants are like, if they exist at all, they will face the collision with technologies and perspectives we cannot imagine. Others find the collision unsettling. It reminds us that nothing lasts forever, not even galaxies. The Milky Way, that has been our home since the first humans looked up at the stars, will eventually cease to exist in its current form. Something new will take its place, but the familiar band of light across the night sky will be gone. Both responses are valid. The universe is what it is, regardless of how we feel about it. Our task is to understand it as best we can and to find meaning in our place within it. The collision between Andromeda and the Milky Way is one more piece of that understanding, one more chapter in the story of the cosmos. As we truly conclude our journey, take a moment to appreciate where you are right now. You are on a planet orbiting a star in a spiral galaxy. That galaxy is currently pristine, with its beautiful arms and central bulge intact. The stars above you are arranged in patterns that have inspired poets and navigators for millennia. All of this will change, but for now, it is here, and you can see it and know it and appreciate it. The collision is coming, but it is not here yet. We have billions of years to study our galaxy, to explore its wonders, and to marvel at its beauty before the transformation begins. So go outside tonight if you can. Look up at the Milky Way if your skies are dark enough to see it. Find Andromeda if you know where to look. And remember that what you see is not static. It is a moment in cosmic time, a snapshot of galaxies in motion, headed toward an encounter that will reshape everything. We are privileged to understand this. We are fortunate to live in an age when science has revealed these truths, and we are connected through the physics that governs the universe to a future billions of years away. Thank you for sharing this journey with me. The cosmos awaits further exploration. There are always more wonders to discover, more questions to ask, more mysteries to ponder. Stay curious, stay humble, stay amazed. The final hour is coming. But we have time, we have knowledge, and we have the capacity to appreciate the grand cosmic drama in which we play our small but meaningful part, until our paths cross again among the stars. And as a final thought, consider this remarkable fact. The light you see when you look at Andromeda left that galaxy when our early human ancestors were just beginning to walk upright on the African savanna. That ancient light has been traveling across the void for over 2 million years, carrying news of a galaxy that was already on its way toward us. By the time that light reaches your eyes, Andromeda has moved hundreds of thousands of light years closer. The collision has advanced, even if imperceptibly from our perspective. Every moment that passes brings the two galaxies slightly nearer to their destined meeting. This is happening right now as you read these words. The gravitational attraction between the Milky Way and Andromeda is pulling them together at this very instant. The dark matter halos are feeling each other's presence across the gulf of intergalactic space. The collision is not just a future event. It is a process already underway, simply not yet visible to our limited eyes. When you look at Andromeda, you are seeing the past, but you are also looking at the future, at the galaxy that will one day merge with ours. Past and future are connected in that faint smudge of light, separated by distances we can barely imagine, and timescales that humble human understanding. This is the power of astronomy. It lets us see across time as well as space. It connects us to the distant past and far future. It shows us we are part of something much larger than ourselves, a cosmic story still being written. The Milky Way and Andromeda have been approaching each other since the universe was young. Billions of years before Earth existed, the trajectory was set. The collision was inevitable from the moment both galaxies formed, bound together by gravity across the cosmic void. We happen to live at a particular moment in this story, billions of years before the climax. We cannot see the ending. We can only imagine it based on our understanding of physics. But we know the ending is coming, as surely as the sun will rise tomorrow. There is something profound about this knowledge. We are mortal beings who have uncovered the fate of our cosmic home. We are brief sparks of consciousness who have grasped truths spanning billions of years. The final hour is coming. May we face it with wonder.